In the last lecture, we talked about bilinear maps as motivation for taking the tensor product of two R modules. And in this lecture, we're going to focus on the actual construction of the tensor product and prove that this is a thing that actually exists. So our main reference for this lecture is going to be Keith Conrad's notes on tensor products, section 3. I prefer this presentation to the one given in Dummett and Foote because this focuses on the case where R is a commutative ring. The situation is significantly more complicated in the general case, and that's the perspective that's taken from the beginning in Dummett and Foote. Okay, so let's say that M and N are two R modules, and let's say that P is some other R module. Why did I separate these? Because M and N are going to be two R modules, and we're going to take the tensor product of these two, and we're going to think about tensor products in terms of maps from M cross N and then also M tensor N to this other R module P. So M and N are getting paired together, and P is just a separate thing. The key property of the tensor product, M tensor N, which we write M O times sub R N, this sub R here emphasizes that we're taking the tensor product of two R modules. The key property that we talked about a little bit last time that is going to be a major thing to keep in mind for this lecture is that bilinear maps B from M cross N to P correspond to R linear maps L from M tensor N to P. All right, so now we'll give a major definition. The tensor product M tensor N is an R module equipped with a bilinear map from M cross N to this tensor product that we'll call tensor, such that for each bilinear map B from M cross N to P, there is a unique linear map L from M tensor N to P that makes the following diagram commute. Okay, what is this diagram? We have M cross N. We have this bilinear map B that we're given that goes to P. We know, what we're trying to show is that there is this R module, M tensor N, and this special bilinear map tensor that goes from M cross N to this R module, M tensor N. And what we want is for this bilinear map B, there's a unique linear map L going from this tensor product down to P, such that if you take any element in M cross N, you take the tensor, and then you apply L, what you get is the same thing as if you had applied this bilinear map B. So what does that mean? L applied to M tensor N is equal to this bilinear map B applied to the pair M comma N for any pair little n in this direct product M cross N. So this is a definition of a tensor product. And I want to note that this definition involves not only a new R module, M tensor N, but also a special bilinear map that goes from M cross N into this new R module. All right, so this is a definition of a tensor product. I'm going to pause and erase, and I'll show you that this tensor product, if it exists, satisfies a certain kind of uniqueness. Then in the next video, we'll show that there really is an R module that satisfies this definition. So first we'll talk about uniqueness of tensor products, and then we'll prove that tensor products actually exist. We'll first talk about uniqueness of the tensor product. So let's suppose that we have T and T prime R modules together with one bilinear map for each, B from M cross N to T and B prime from M cross N to T prime. And these maps and these R modules will be such that the pair TB and the pair T prime B prime both satisfy the definition 3.1 that we gave earlier. They satisfy this universal mapping property of the tensor product, saying that for each bilinear map from M cross N to P, there exists a unique linear map making the diagram commute that we wrote down before. So what are we going to see? We're going to see that in this case, T and T prime are isomorphic R modules. In fact, we're going to see more. We're going to see not only that T and T prime are isomorphic R modules, but that these special bilinear maps, B and B prime, are related to each other as well. All right, so since TB, this pair, satisfies the definition of a tensor product, we have some particular bilinear map from M cross N to some R module, that is B prime, which goes from M cross N to T prime. This must factor uniquely through T. So what does that mean exactly? That means that there exists a unique linear map that goes from T, this thing that satisfies the definition of a tensor product, to T prime, which is like that R module P from the definition. And this unique linear map makes it so that this diagram commutes. Which diagram? If you take M cross N, you apply B to go up to this R module T, then there exists this unique linear map F so that you apply F after that, and you end up in T prime. And what you get is the same thing as if you had applied this special bilinear map B prime to M cross N. So given B prime, there is the existence of this F. We're going to come back to this, so we're going to label this diagram star. So T and B satisfy the definition of a tensor product, but so do T prime and B prime. So let's do the same thing with the role of T and T prime switched. So since T prime B prime satisfies this definition 3.1, the map, bilinear map B from M cross N to T factors uniquely through T prime. Sorry, there's a typo here. And now my marker is not cooperating, so factors uniquely through T prime. That means there exists a unique linear map F prime from T prime down to T such that this diagram commutes that we'll call star star. So you take M cross N, you apply B prime, then you apply this unique linear map F prime, whose existence is guaranteed by the definition of a tensor product. And what you get when you compose these maps is the same thing as if you had just applied the bilinear map B to your pair in M cross N. And now the idea is we're going to combine these two diagrams, star and star star, together to get a new commutative diagram that is going to show us that, in fact, we have an isomorphism between T and T prime. So I'll pause and erase, and I will show you the rest of this uniqueness argument. We combine these two commutative diagrams, star and star star, to get another one where we have M cross N, we apply B to go up to T, or we apply B prime to go to T prime, then we have this map F. But now if we just put this commutative diagram underneath this one with this B prime map in common, we could take from M cross N, apply B prime, go over to T prime. We know that we have this linear map F prime so that this bottom triangle commutes, where we apply B down at the bottom to get to T. And now we can just leave out the middle. Like, we don't have to write T prime in here. We can just compose this map from T all the way down to T, where we do F and then we do F prime. And this gives a commutative diagram where you start with M cross N, you apply B, you go up to T, you apply F prime following F, you go down to T, and what you get is the same thing as if you had just applied B at the beginning. All right, what does this map F prime following F have to satisfy? So we're going to use the definition of the tensor product, the fact that the pair TB satisfies definition 3.1, to see the answer. So I'm going to pause and erase to get more space, and we'll finish up this argument. We know that we have this linear map F prime following F from T to itself that makes this diagram commute? Well, since the pair TB satisfies definition 3.1, this definition of a tensor product, there is a unique linear map that fits into this vertical space, this from T down to T here, and makes this diagram commute. But we can think of one linear map that makes this diagram commute, the identity on T. That is a linear map that makes this diagram commute. So by this uniqueness, f prime following f is the identity on the R module T. All right, so now let's redo this whole argument again. And instead of taking this map from m cross n, b up to T, going down to T prime, and then going back to T, what we'll do is just stack the other way and take b prime up to T prime, then apply b in the middle, b prime again down here to T prime. And you'll see that there was nothing special about T or T prime. What this is going to tell us is that f following f prime is the identity on the R module T prime. So what does that mean? That means that this R module homomorphism f from T to T prime has an inverse. So this R module homomorphism f, it's injective and it's surjective. It is an R module isomorphism. We see more than that. Applying this kind of uniqueness argument, you apply B, then you apply F, and at every pair of M cross N, you get the same thing as if you applied B prime. Well, there's a unique map F that makes this commute. And we can similarly argue that this means that F following B has to be equal to B prime. So what we've seen is that T and T prime are isomorphic R modules, that F is an isomorphism between them. And more than that, that these special bilinear maps satisfying the definition of the tensor product from M cross N to T and from M cross N to T prime are related to each other by this isomorphism F. So in the next video, we'll actually show that given two R modules, M and N, there does exist a pair T comma B that satisfies the definition of a tensor product.